Okay, in this lecture, we will delve into the conditional distribution of points in Poisson processes. Let's set the stage. We're working in a d-dimensional Euclidean space, which we denote as script x equals r to the d. We have a Poisson point process S, which maps from our sample space omega to script x raised to the n, meaning it's a sequence of points in script x. This process is characterized by an intensity measure lambda mapping from the Borel sets of script x script b of script x to the non-negative real numbers r plus. Associated with S is its counting process n, which maps from omega to z plus non-negative integers raised to the power script b of script x, telling us how many points fall into any given Borel set. Now consider a proposition, let k be any positive integer. We have our Poisson point process S with its intensity measure lambda. Let A be a finite partition of a bounded set B in script B of script X. This means A consists of k disjoint sets A1 through AK, whose union is B. Also let N be a vector of k non-negative integers N1 through Nk that sum up to a non-negative integer M. The proposition states that the probability of observing n of A1 equals N1, n of A2 equals N2, and so on till and n of AK equals Nk, given that the total number of points in B, n of B is M, is given by the multinomial probability M choose N1, N2, and so on till Nk times the product from I equals 1 to k of lambda of A I divided by lambda of B all raised to the power Ni. This is our equation 1. Let's walk through the proof from the definition of conditional probability and recognizing that the event n of A1 equals n and so on till n of AK equals Nk is a subset of the event n of B equals M. Since the AI's partition B and the NI's sum to M, we can write the conditional probability on the left-hand side as a ratio. This ratio is the probability of n of A1 equals N1 and so on till n of AK equals Nk and n of B equals M, divided by the probability of n of B equals M. Since the joint event for the AIs already implies n of B equals M, this simplifies to the probability of n of A1 equals N1 and so on till n of AK equals Nk, divided by the probability of n of B equals M. Continuing with the proof, we leverage the complete independence property of Poisson processes and the fact that their marginal distributions are Poisson. So the joint probability of the counts n of A1 through n of AK, since the AI are disjoint, is the product of their individual Poisson probabilities. Also, remember that the intensity measure is additive over disjoint sets, meaning lambda of B equals the sum from I equals 1 to k of lambda of AI. Using these facts, we can rewrite the right-hand side of our previous equation. The numerator becomes the product from I equals 1 to k of E to the power minus lambda of AI times lambda of AI to the Ni over Ni factorial. The denominator is e to the power minus lambda of B times lambda of B to the M over M factorial. After simplifying this expression by cancelling out the e terms, since sum of lambda of A, I is lambda of B, and rearranging the factorials, we arrive precisely at M choose N1 and so on till Nk times the product from I equals 1 to k of lambda of ai over lambda of b raised to the ni. Let's pause for a reminder. We have our Poisson point process S with intensity measure lambda and counting process N, and A is a k set partition for a bounded set B. First, if we define P sub I as lambda of ai divided by lambda of b, we can see that the vector P1 and so on till Pk forms a probability distribution as its components are non-negative and sum to 1. This is an element of script m of the set of integers from 1 to k. We can interpret P sub I. It's the probability that n of ai equals 1, given that n of b equals 1. This is also the probability that the absolute number of points from S in ai is 1, given that the number of points from S in B is 1. If we know there is exactly 1 point from S in B, let's call it S1 without loss of generality, then P sub EI is simply the probability that this point S1 is in AI, given that S1 is in B. Continuing, if we are given that N of B equals Ni, and if we denote the points of S in B as S1 through Sni, so S intersect B is the set S1 and so on till Sni. The probability that N of ai equals Ni, given N of B equals Ni, is P sub I raised to the Ni. This represents the probability that all Ni specific points fall into ai, given they are in B. That is, it's the probability of the intersection from j equals 1 to ni of the event. Sj is in ai, given that the set S1 and so on till Sni is S intersect B. This seems to simplify to the product from j equals 1 to ni of the probability that Sj is in ai given Sj is in B. Second point of reminder, we can rewrite our equation 1 using these pi's, recognizing it as a multinomial distribution. The probability of n of a1 equals n1 and so on till n of ak equals nk, given n of b equals m, is m choose n1 and so on till nk times p1 to the n1 and so on till times pk to the nk. Continuing our reminder, third, for any finite set f of natural numbers with size m and a vector n in z plus to the k that partitions m, let's define script p sub k of f, n as the collection of all k partitions e of f, such that the size of ei is ni for each I from 1 to k. Then the multinomial coefficient m, choose n1 and so on till nk actually counts the number of ways to partition m distinct items points into k distinct groups with sizes n1, 1 and so on till nk, that is m choose n1 and so on till nk equals the cardinality of script p sub k of the set of integers from 1 to m with partition sizes n. Fourth point of reminder, if we define ei as S intersect ai and E as S intersect B, recall that the event n of ai equals ni, the same as the cardinality of S intersect ai equals ni. Hence, we can write the conditional probability P of the intersection from I equals 1 to k of cardinality S intersect ai equals ni, given cardinality S intersect B equals m, is m choose n1 to nk times p1 to n1 dot 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 pk to nk. This can be expanded as the sum over all partitions E in script pk of S intersect B, n of the product from I equals 1 to k of the product over all Sj in Ei of P of Sj in Ai given Sj in B. Continuing the reminder. Fifth, when n of B equals m, let's denote the set S intersect B by F, which is S1, and so on till Sm without loss of generality. We further observe that when n of ai equals ni for all I from 1 to k, then the collection S intersect A1 and so on till S intersect k forms a k partition of S intersect B according to the counts n. This means it's an element of script P sub k of S intersect B n. Therefore, we can rewrite the event intersection from I equals 1 to k of n of A, I equals ni, which is the same as intersection from I equals 1 to k of cardinality S intersect A, I equals ni, as the union over all distinct partitions E in script pk of S intersect B n of the event intersection from I equals 1 to k of S intersect AI equals EI. That is, we can write the conditional probability conditioned on S intersect B being a specific set F of m points as the probability of the intersection from I equals 1 to k of n of ai equals ni given n of b equals m is the sum over E in script pk of f n of the probability of the intersection from I equals 1 to k of S intersect ae equals E, I given S intersect b equals f. This in turn is the sum over E in script pk of f with partition sizes n1 to nk of the probability of the intersection from I equals 1 to k, and for all Sj in Ei, that Sj is in Ai given S intersect B equals f. Continuing the reminder, sixth, if we equate the right hand side of the above equation from the previous slide, which express the multinomial probability term wise with the sum we just wrote, we deduce an important property conditioned on in specific points falling inside the window BIE S intersect B is a fixed set F of m points. The conditional probability of each of these points falling into a particular partition AEI is independent of where the other points fall, and this probability is given by Pi, that is the probability of the intersection from I equals 1 to k, and for all Sj in Ei, that Sj is in Ai given S intersect B equals f is the product from I equals 1 to k of the product for Sj in Ei of P of Sj in Ai given Sj in B. This simplifies to the product from I equals 1 to k of Pi to the ni, which is the product from I equals 1 to k of lambda of ai over lambda of b raised to the ni. What this means is crucial. Given that there are exactly m points in the window B, the locations of these m points are independently and identically distributed within B, following a distribution proportional to the intensity measure lambda. That is, the probability density for a point to be at x within B is lambda of dx by lambda of b or lambda of x dx by lambda of b if a density lambda of x exists. Continuing the reminder, seventh, if the Poisson process is homogeneous, meaning lambda of x is a constant, then this conditional distribution of points within the window B becomes uniform over B. Eighth, a summary for a Poisson process with intensity measure lambda, and for any bounded set A in script B, the number of points n of A in that set is a Poisson random variable with parameter lambda of A. Crucially, given the number of points n of A, the locations of all the points in S intersect A are independent and identically distributed IID with the probability density function given by lambda of x divided by lambda of A for all x in A, assuming an intensity density lambda of x exists. As a final reminder, let's consider how to simulate a homogeneous Poisson point process. Suppose we want to simulate a two-dimensional homogeneous Poisson point process with a constant density lambda within a unit square. Say A equals the Cartesian product of the closed interval from 0 to 1 times the closed interval from 0 to 1. The first step is to generate the random variable n of A, which represents the total number of points in the square. N of A will take a value n with probability e to the minus lambda times lambda to the n over n factorial. Since the area of A is 1, lambda of A is just lambda. Next, for each of these n of A which equals n points, we generate its location open interval from xi to yi within the square uniformly at random and independently of all other points. That is, x a vector of nx coordinates and y a vector of ny coordinates are independent IID uniform sequences. Each component drawn from the closed interval from 0 to 1.
Now a corollary for a homogeneous Poisson point process on the half line. Let S tilde be the ordered set of points S sub n in R plus for n in natural numbers. We can write the conditional density of the ordered points S sub 1 and so on till S sub k, given the event that nt equals k, meaning k points in the interval open from 0 to t closed as the joint density of the order statistics of KIID, uniformly distributed random variables over open interval 0 to t closed. Specifically, the density f of S sub 1 through S sub k given nt equals k evaluated at t and so on till tk is k factorial times the indicator that 0 is less than t1, which is less than or equal to t2, and so on till tk, which is less than or equal to t, all divided by t to the power k.
Let's look at the proof of this corollary. Given that nt equals k, we can denote the k points of the Poisson process that fall in the interval open from 0 to t closed by S1 and so on till Sk. From our previous reminder, we know that these S11 and so on till Sk are IID and uniformly distributed in the interval open from 0 to t closed, conditioned on nt equals k. Hence, we can write the joint cumulative distribution function f of S1 through Sk given nt equals k evaluated at t1 and so on till tk. This is the probability of the intersection from I equals 1 to k of the event. Si is in the interval open from 0 to t I closed given nt equals k. Due to conditional independence, this becomes the product from I equals 1 to k of the probability that Si is in the interval from 0 to t I closed, given Si is in the interval from 0 to t closed. This simplifies to the product from I equals 1 to k of ti over t times the indicator that 0 is less than ti, which is less than or equal to t. Therefore, for 0 less than t, 1 less than t, 2 and so on till tk less than 1, this should be tk lesser than t for consistency with n, t equals k. And for sufficiently small he1 and so on till hk, we have the probability of the intersection from I equals 1 to k of Si being in the interval open from ti to ti plus hi closed is approximately the product from I equals 1 to k of hi over t. Continuing the proof, since S1 through Sk are conditionally independent given S intersect A equals the set S1 and so on till Sk, where A is our window interval from open from 0 to t closed, it follows that for any permutation sigma mapping integers 1 to co, k to integers from 1 to k, the conditional joint distribution of S sigma 1 and so on till S sigma is identical to that of S1 and so on till Sk given S intersect A is the set S1 and so on till Sk. Furthermore, we observe that the order statistics of S sigma 1 and so on till S sigma are identical to the order statistics of S1 and so on till Sk. Therefore, we can write the following equality for the events. The intersection from I equals 1 to k of S sub I, the ith ordered point, is in the interval open from ti to ti plus hi closed is equal to the union over all permutations sigma of integers from 1 to k to integers from 1 to k of the event intersection from I equals 1 to k of S sigma E is in the interval open from ti to ti plus hi closed. The result for the joint density of the ordered statistics then follows because there are k factorial such permutations and each specific ordering, if the ti are already ordered, corresponds to one of these permutations of the underlying IID uniform variables. This concludes our discussion on the conditional distribution of points in a Poisson process.